What if I told you that you could generate electricity not when the sun is shining, but when the sky is dark? Imagine a panel that doesn't just go silent at night, but actually works in the darkness. That sounds like science fiction, but recent research is paving the way for exactly that: reverse photovoltaics, or what some call anti-solar cells or thermoradiative cells. Rather than absorbing sunlight, these devices emit infrared radiation toward the cold of outer space, and in doing so, convert that energy loss into usable current. Welcome to a world where darkness becomes a source of power. Every conventional solar panel operates in one direction. It absorbs photons from sunlight, excites electrons, and those electrons flow and produce current. But at night, when there's no incoming sunlight, those panels lie dormant. The dream of continuous, 24/7 renewable energy has always hit a major barrier: storage. Batteries, pumped hydro, supercapacitors, all are expensive, lossy, require maintenance, and are capacity limited. What if instead, the panel itself could keep producing, leveraging the natural thermodynamic imbalance between a warm surface and the frigid depths of space? The principle is based on radiative cooling. Any object warmer than its surroundings emits infrared radiation. During the day, Earth absorbs solar energy. During the night, Earth radiates heat into space. If you place a panel engineered to emit more efficiently into cold sky, it can shed heat preferentially outward. The temperature difference between the surface and the cosmic background becomes its driving force. That heat flow, from warm to cold, can push charged carriers in specially designed semiconductors, producing a small but positive voltage and current. In effect, energy that would otherwise be lost is harvested. In lab prototypes, researchers use materials such as mercury-cadmium telluride (HGCdTe) and other narrow bandgap semiconductors tuned for infrared emission. The panel is engineered to emit strongly in specific wavelengths while suppressing unwanted modes. When the panel surface is warmer and facing the cold sky, electrons in the material lose photons radiatively into space, and this emission induces a flow of charge back toward the panel's contacts, producing power in reverse compared to daytime photovoltaics. To date, these devices are still nascent. The experimental systems generate very modest power densities, on the order of tens of milliwatts per square meter in some experiments. But this is enough to light a low-power LED, run small sensors, or trickle charge batteries in off-grid settings. Despite the low output at present, the physics is validated and steady improvements are happening. In fact, theoretical work suggests far more aggressive power densities might be possible with optimized emitters, materials, and thermal design. For instance, in one study optimizing emitter spectra and thermoelectric coupling, models predict power densities exceeding to W per square meter at night under ideal conditions. This is more than 2 orders of magnitude above early experimental values. ARC-7 of their theoretical design effort proposes combining daytime solar harvesting with nighttime thermoradiative emission, a hybrid 24/7 generator. Their modeling suggests the system could reach daytime efficiencies around 12.6% and nighttime power outputs up to 10.8 W per square meter in ideal conditions. ARC-7, if realized, that would rival many existing renewable energy systems. Why is this idea so compelling? Because it offers a route to continuous renewable energy without relying solely on storage. In ideal form, such panels could reduce or eliminate battery banks for many use cases, especially low-power devices, remote sensors, off-grid lighting, or IoT systems in places where installing batteries is problematic. No sunlight? No problem. Clouds, storms, polar nights, so long as the sky is colder than the emitter surface, energy can flow outward and be harvested. For truly dark, clear nights, the contrast is greatest in output peaks. There are engineering challenges, of course. Thermal insulation is critical. The panel must be isolated from warmer surroundings. to minimize parasitic conduction and convection losses. Radiative emissivity must be carefully tuned to favor the right infrared bands. Any haze, atmospheric water vapor, or cloud cover can dampen infrared transmission to space. The semiconductors must maintain low recombination losses and match the spectral emission band. The contact and electrode design must not block or interfere with emission. Also, scaling a laboratory prototype to large area modules cost-effectively is non-trivial. Despite the hurdles, this concept is already drawing attention. For example, Stanford researchers have built prototype panels that generate small power output at night by radiative emission. Media outlets have showcased novel solar panels that work at night and solar power at nighttime as emerging breakthrough technologies. One video titled "This Panel Generates Electricity Without the Sun" explores how such panels could complement daytime photovoltaics. Another video, "Novel Solar Panels That Work at Night," gives a broad overview of these reverse devices. Yet another, "Engineers at Stanford Develop Solar Panels Work at Night," shows a real prototype in practice. In terms of application scenarios, imagine rural or remote regions lacking grid infrastructure. A rooftop installation could absorb solar energy by day and at night emit heat to generate additional power rather than relying entirely on batteries. Sensors, IoT nodes, weather stations, remote lighting, or environmental monitors could get a continuous trickle of power. In space applications or lunar bases, where sunlight cycles are extreme, radiative emission toward cold deep space would be especially advantageous. On Earth, high altitude, dry sky regions, deserts, plateaus offer the best conditions for clear line of sight to the cold sky over time. Advancements in material science, photonic engineering, nanophotonic emitters, and hybrid panel design should push the performance upward. If hybrid daytime, nighttime modules become practical, we may see solar systems that never truly rest. The future of renewable energy might not only chase photons, it might also race the darkness. When you look up at the night sky, remember that inky black canvas isn't just empty. It's a cold sink, a giant heat reservoir we can tap into. And as researchers refine the technology, we may soon live in a world where your roof is not just a solar collector, but also a nighttime generator, harvesting energy from the silence of space.